Now that we know about inverse matrices and how to find them, we want to recognize that we can actually solve systems of linear equations using the inverse matrix, and we can do it pretty simply. And here's why. So let's say that we have a linear system, 7x plus 5y equals -4, and -6x plus 3y equals -33. Remember that we can express this system in terms of a matrix vector product. So we can take the coefficient matrix of the system, we take the coefficients on x and put them in the first column, 7, -6, and then the coefficients on y, 5 and 3, go in the second column. This system is the same as saying this matrix gets multiplied by the vector that includes the components, which are the unknown variables x and y, and that's set equal to this solution vector, -4, -33. So these two things are saying the same thing. What we want to solve for is this vector here, xy. We want to know the value of x and the value of y. We'll realize that we could actually rewrite this in a different way. We need to recognize that we have a matrix here, so let's call that matrix A, multiplied by a vector, which we'll call the vector x, and that's set equal to this solution vector, which we'll call the vector b. So we've got a matrix vector product, and then that's set equal to b, ax equals b. If we take the inverse matrix of both sides, we multiply both sides by the inverse matrix, here's what we learn. So we get the inverse matrix, A inverse, times A, times the vector x is equal to A inverse times the vector b. On the left-hand side, when we do that, A inverse times A, we know is essentially equal to 1 in matrix form. It's the identity matrix. So this A inverse A really simplifies just to the identity matrix. So we get I times the vector x is A inverse times the vector b. And we know that multiplying the identity matrix I doesn't ever change the value of the vector or the matrix. It's like multiplying by 1. So we could just simplify this left-hand side and write the vector x is equal to A inverse times the vector b. And here is really our key formula when it comes to solving a system using the inverse matrix. Remember that this vector x here represents this vector xy. Xy are the values we want to find, so the vector x is really what we're trying to solve for in this system. X and y are the unknown values. And we're saying that that vector x is equal to the inverse matrix multiplied by the solution vector b, -4, -33. So in other words, in order to find the solution to the system, x and y, in order to find the vector x, all we need to do is find the inverse matrix, the inverse of this matrix A, and then multiply it by the vector -4, -33, and we'll have our solution to the system. So the first thing we have to do, obviously, is find A inverse. And there's a couple ways we could do that. We could use the determinant formula that we learned before, or we could augment the matrix A with the identity matrix and put it into reduced row echelon form to find A inverse. Let's go ahead and just use the determinant formula. So let's say that A inverse is going to be equal to, and then our determinant formula is always 1 divided by the determinant of the original matrix. So the determinant of A here is 7 times 3, which is 21, minus 5 times -6. Well, that's -30. So minus a -30 is a plus 30. And then we multiply that by this same matrix A, except that we flip the positions of the 7 and the 3. So we get 3 and 7. And then the 5 and the -6 stay where they are, except that we change their signs. So +5 becomes -5, and -6 becomes +6. And then here we'll get 1 over 51, so 1 over 51 times the matrix 3, -5, 6, and 7. So then the inverse matrix is going to be 1 over 51 times 3. That's 3 over 51, or 1 over 17. -5 times 1 over 51 is a -5 over 51. 1 over 51 times 6 is a 6 over 51, but 6 divided by 3 is 2, and 51 divided by 3 is 17, so 2 over 17, and then 1 over 51 times 7 is a 7 over 51. So this is our inverse matrix, A inverse, And then if we want to solve for x, which is our unknowns, we just multiply this matrix by the solution vector -4, -33. So we can say the vector x is equal to the inverse matrix multiplied by -4, -33. So the result here then, for the vector x, we'll get 1/17 times -4, and then plus a -5/51, so we'll just say minus 5/51 times -33. Then we'll get 2/17 times a -4, so 2/17 times -4, plus 7/51 times -33. When we multiply, let's do this up here. When we multiply -4 times 1/17, we'll get -4/17. Here, our -5/51 and our -33, the negative signs will cancel. We'll be left with a positive. We can divide 33 and 51 both by 3. So 33 divided by 3 gives us an 11. 51 divided by 3 gives us a 17. So we have 5 times 11 is 55/17. So plus 55/17. Then here, 2/17 times a -4 is going to be -8/17. And then because we have our minus sign here, we'll end up with a minus. Again, we can say 33 divided by 3 is 11. 51 divided by 3 is 17. So we cancel that common factor. 7 times 11 is a 77. So we end up with 77/17. And now, -4 plus 55 is a 51. So we get 51/17. And then -8 minus 77 is a -85. So -85/17. And 51/17 is 3. -85/17 is a -5. So the vector x is the vector 3, -5. Let's just go ahead and write x equals 3, -5. Or we could say the vector xy is equal to 3, -5. So 3, -5 is the solution to our system, x equals 3 and y equals -5, which we found simply by taking the inverse of our coefficient matrix A to get A inverse, and then we multiplied that coefficient matrix by the solution vector, in this case -4, -33, to get the result. And one of the reasons this is so useful is not just for finding the one-off solution to one system in particular, but now that we have an inverse matrix, we can change our values over here, -4 and -33. We can change these to any two values that we'd like, and all we have to do to find the values x and y that satisfy that new system is multiply this inverse matrix we already found by that new solution vector. So this gives us something we can use repeatedly, even if we change the solution vector over and over, to find the solution xy that satisfies the system regardless of the values over here on the right-hand side.